All right, today we're going to be talking about graph theory. We're not going to be getting into any coding today. We're just going to go completely conceptual. So I'm not going to be teaching you guys for discrete math this upcoming semester, but graph theory is kind of my favorite topic from CSCI 26. So I'm going to cover it today, in part because it is a data structure. A graph is a data structure. Okay? So how many people here know what a graph is? Show of hands on chat. Yes. All correct answers. A giraffe is, in fact, a tall animal. Look at this graph. For those of you on the internet, there you go. There's a recursive Nickelback. Okay. Anyway. Graph paper, right. The graph is a visual representation of statistical numbers. Yes, all of you are right, but we are no, none of that is the graph that we're talking about today. So nope, none of that is accurate. What we are talking about is something that looks like this. So a graph is a connection, a series of connections between vertices. The connections we call edges, the vertices we call vertices or nodes sometimes. So anytime you see something that looks like this, it is a graph. In fact, you've already done one graph, which is a binary tree. Binary search tree is a graph. A heap is also a binary tree. It's not a binary search tree, but it's also a graph. It's a specific kind of graph called a directed acyclic graph because it's got arrows and it has no loops within it. This is cyclic. You can see there's like a loop here within it. What do these things mean? What does this graph mean? Well, it's hard to say because without any context, this could be anything, right? Graph theory is a very broad domain. Like you can get your doctorate in graph theory. In fact, the person who taught my discrete math class was a math professor who specialized in graph theory and taught at UCSD. We didn't call it 26, but they taught CSCI 26 and didn't do any coding. There was no coding. It was just 2 quarters of just pure math. And that was rough. I highly recommend you guys do coding. Even if your professor doesn't, I would try to write programs because going all of summer and all of fall without writing a program and then going to 45 in the spring is going to be a tough gap to make up. So I would recommend maybe taking game dev. I teach IS50A in July. Taking that will keep your programming skills up. It's every day in July, noon to 4 o'clock, Monday through Friday. So we do game development every day. We play games, we talk about games, we make games. So if you guys are interested in making video games, even if you hate video games, a lot of people have never played a video game in their life, they've still done well in the class because you learn all sorts of interesting technical skills. You also learn about human psychology and physics and all sorts of other things too. Anyway, so graph theory, yeah, it's just pure mathematics, right? And in fact, we're not going to be doing any coding of it today. I'll show you a little bit of code, but we're not going to be actually on the server at all today. We're just going to be talking math. So what these things could represent could be anything. Like I said, it could be people. Like each vertex could represent a person. And the edges could represent a friend. So for example, who here has friends in this class? Show of hands and tell me who your friend is. So we've got Lamar over here, and Lamar is friends with Bean, right? Who else are you friends with, Lamar? Nobody? Okay, no, I'm kidding. Quite a few. Just name one. Just name a person. And then we can have like Olson over here, and Olson is friends with, I don't know, Orozco here, and Orozco and Bean and Olson are all friends with Viale here, and Moran is friends with Bean and Olson, and Bros Santiago. Okay, so Santiago only has 2 friends, unfortunately. So Santiago, you can see, is friends with Lamar, and Santiago is friends with Moran, and he's friends with nobody else in the class. Sorry. Olson, however, has 4 friends. Olson is friends. You can see here, Olson is friends with Bean. He's friends with Moran. He's friends with Viale. He's friends with Orozco. So the degree of this vertex, we want to introduce some terminology. The degree is 4. Orozco's degree is 2. Viale's degree is 3. Bean's is 4. And Lamar's is 2. And Santiago's is 2. And Moran's is 3. And so that's basically your friend count on Facebook, right? So if you want to think of Facebook or other social media, the reason why it's called a social network is, look at it, it's a network. And this is literally, it's graph theory, okay? So, the friends you have, it's bidirectional if it's friendship. If you're following somebody, it's unidirectional. You can follow somebody without them following you back. But friendship is bidirectional. Notice there's no arrows on this, at least, yeah, on the graph itself. So if you friend somebody, they friend you back. And so the lines here could represent friendship. They could represent all sorts of things. So another graph would be, for example, Hollywood loves graph theory, by the way, because it looks cool. Nobody knows what's happening here, but it looks super cool. It's actually a really easy problem to solve, but it looks like MIT math professors worked on this puzzle for 2 years, and it's a trivial problem. It takes like 10 minutes to solve. Here's a graph, the internet. This is the internet in 1973. This is every machine on the internet. This is the entire internet. Back then it was called ARPANET. It wasn't rebranded the internet until I think the early 90s, if I'm remembering right. And you can see they've got PDP-10s, PDP-11s, attached to the different... there's UC Santa Barbara, UC San Diego. Woohoo, we got San Diego's on there. London is attached to the internet. This is a graph. And so each node on the graph is like a server or a router or something. And the lines represent like actual physical data lines between them. Ames up in San Francisco, probably. Stanford is connected to Ames. That makes sense. Stanford has a line running down to USC. USC runs to Rand. Rand connects to UCSD. UCSD connects to UCLA. So on and so forth. Okay. So, I guess USC is on here twice. Look at that. You got USC TIP and USC ISI. Interesting. You got an IBM 360 system. Yeah. So cool. So the edges just represent some form of connection, some form of maybe relationship. There's no inherent meaning to a graph. Like if all you did is show me a graph, I'm like, I don't know what that means, because it's so broad, right? They could be logic circuits connected together. They could be state adjacency graphs. For example, one famous problem in graph theory is the graph coloring theory, which is if every state could be represented as a regular polygon, none of this weird like Michigan stuff where it's split into two, or there's some weird like state boundaries where like one state's inside of another state. Like none of that stuff, just like regular polygons. Is it possible to color the map so that you have no touching colors, right? So that California and Nevada both are not red, right? Nevada and California are two different colors. And so you can see here, this map is represented as a graph, and then they color the graph. And we have, in fact, proven you can color any regular map like that using only 4 colors. Is in fact proven by a computer. Is one of the first, if not the first, computer-proven proofs. Was they had a supercomputer chewing on this problem for a while. I proved it. A friend of mine at Microsoft, his job interview question. By the way, a lot of job interview questions come from graph theory. It's quite common. In fact, I would say probably the 2 most important classes for job interview computer science questions are CSCI 41 and CSCI 26. Recursion, dynamic programming, bit fields, trees and graphs. It's a whole chapter of cracking the coding interview. All of chapter 4 is trees and graphs, right? Stacks and queues, linked lists, recursion, dynamic programming. Dynamic programming will be our last lecture. Yeah, that's object-oriented programming, databases, arrays and strings. Yeah. So now, a friend of mine at Microsoft, his job interview question that he asked like basically everybody for like 10 years or something was, given a map of the United States and every state having letters in it. California has CALIF, Nevada, NAV. By moving from state to state to state using the adjacency graph that we have here, what is the biggest word you can spell? You can pick a letter out of any of the words in any of the letters in California, and then you move to Nevada, you pick out a letter there, and you move to Utah and pick out a letter there, right? So you could spell like C from California, A from Arizona, N from Nevada, but it doesn't have to be the first letters, but that spells the word can, right? What is the biggest English word you can spell using maybe a graph of the contiguous 48 states? Interesting problem. Yeah, it's a cool job interview problem, and you get like, I don't know, 15 minutes or something like that. You sit in front of a whiteboard, and it's like, go. And he doesn't expect you to like solve it. Like it's more like whenever you do a job interview, you want to talk out loud and think about like, how should I start approaching this problem? Should I start with the English language and see if the English language can, maybe this is a finite state machine. Let's see. But, maybe I can just run through every word in the English dictionary and see if it gets recognized by the finite state machine. It's a non-deterministic finite state machine. I see. And you talk out loud, you kind of sketch things, and then the job interviewers look at the way that you think and look at your knowledge base and look at how you try to solve problems and things like that. I asked him, like, did anyone ever actually solve it? And he said, yeah, like once the guy wrote an entire solution, like with an entire like finite state machine, like code and all this stuff in the 15 minutes or whatever he had. I was like, did you hire the guy? He's like, oh, hell yeah. Normally though, they just want to, hear you kind of reason it out and think about how you're going to solve these things. Graph theory is extremely common. Okay. So, it's also used in shortest paths. So interesting. So the Google Maps or something like that, right? When you navigate from here to Vegas, it's going to do a shortest route to Vegas. It's not going to navigate you from Fresno to Atlanta to New York to Vegas. You know what I mean? Like whenever you use Google Maps, at least it used to give you the shortest distance. Now they do this like thing with like, oh, your carbon, minimize your carbon, whatever. But in general, like when you do navigation, like GPS navigation, it's going to find the shortest route between, point A and point B. And that is a graph theory problem. Okay. So here we've got a map of Minneapolis, St. Paul, Madison, Wisconsin, Lansing, Michigan, and we've got routes between them. So I'm going to put some numbers on here, and I'm just okay. Let's try that again. I'm going to put some numbers on here, and the numbers are how many hours it's going to take to drive. So it's 20 hours to drive between St. Paul and Lansing. So yes, edges can have numbers on them. So a vertex represents that St. Paul there. It's not, corresponding exactly to the location in real life, but it doesn't matter. It's just a math problem. So let's say it's 10 hours to Des Moines, and it's 5 hours to Madison, and 6 hours this way, and 20 hours this way, and 3 hours this 1 hour this way, and 10 hours this way, and 5 hours this way, and 10 hours this way, and 7 hours this way. Okay. So this is actually one of your quiz problems for today. Given this map, the quiz question's not this one exactly, but let's see if you guys can solve it. Given this map, and the numbers are hours, right? It's not miles. It's not 20 miles from St. Paul to Lansing. It's 20 hours. Distances in time are often more meaningful, right? Because Los Angeles and Orange County are physically quite close to each other, but if you want to drive it, it takes like an infinite amount of time because LA traffic is literally a black hole of existence. So anyway, so these numbers are in time, hours. What is the minimum number of hours that it can take to drive from Minneapolis, St. Paul? Let me put here's the start up here. To drive from Minneapolis, St. Paul to Columbus, Ohio. This is the end. I'm going to pause the recording, and you guys think about it and come up with a number. How many hours is it going to take? Shortest route. Sorry, I'm missing a number. I'm missing a number between Madison and Lansing. Let me fix that real fast. You will be, I don't know, 6 or something. Okay. Continue. Least number of hours to travel from St. Paul to Columbus. All right, so we got some 21s. We got some, got 133, but that was assuming you can't drive through water. No, it's not a trick question. Just assume there's a bridge or, like the route actually goes around it. Remember, this is an abstraction, right? It's not like there's a giant red line in real life, right? So the fastest route, maybe you have the Harry Potter car, exactly. The fastest route that I can see, tell me if I'm wrong, is 5 plus 6 plus 1 plus 7. And so that's 11 plus 8 is 19. I think 19 hours is the shortest drive between Minneapolis, St. Paul, and Columbus, Ohio, given the graph here. Okay. Do you guys concur? All right. Cool. And so that is a shortest paths problem. And shortest paths is incredibly common. It's in video games, if you guys want to make video games, consistency achieved. Good. In video games, you have an AI, and the AI is trying to attack you. So there's a variant of this algorithm called A-star that we use in video games. And so it'll path towards you via the shortest route. And it will dynamically, depending on your settings, dynamically recalculate the shortest path. So like if you move a table, it'll block it off. I cleared a combat encounter you're not supposed to fight in Kingdom Come Deliverance by standing on a fence post and shooting the people, and I aggroed this entire army. Like, you're not supposed to fight it. And I had 500 guys. It wasn't 500. It was 40 guys coming at me. And then I stood on the other side of the fence post, and they all pathed back around the fence and came at me on the other side. And I jumped over the fence post, and they turned around and went back, and I just sat there glitching the AI over and over again because they're always trying to find the fastest path to me. And so by doing this, I just kept them running and never attacking. There were a couple guys with bows and arrows that were kind of annoying. Those guys I had to kill first. But all the melee guys, I could just hop back and forth over this little obstacle, and then the shortest route would change every time, and I could just keep them infinitely away from me by doing so. So, yeah, video games use shortest path all the time. Google Maps. If you're sending a packet on the internet, the way that your packets get routed on the internet uses a shortest paths algorithm. Not the longest path, ideally, although with Comcast it feels that way sometimes. All right. So how do we actually hold a graph in computer science? So this is a method that is easy to understand, but we don't actually use this. So usually we don't use this. But first of all, see if you can understand this. So on the left-hand side here, we have a non-directed graph. So person 1 is friends with person 2. Person 5 is friends with person 4. Person 3, person 1. And so if you look at row 1, column 2, see there's 1 there. If you look at row 2, column 1, there's a 1 there. The 1 means they're friends. And it's actually symmetrical. If you look at, see if I can angle it right. Yeah. If you look at the matrix, it's actually symmetrical around the diagonal. Because if person 1 is friends with 2, then person 2 is friends with 1. And so row 1, column 2, and row 2, column 1 are both set to be true. You guys see that? And so if all I showed you, if I covered up the graph, right, and all I showed you was the matrix, you would be able to figure out if person 5 is friends with person 1 by going to row 5, column 1, and you're like, oh yeah, there's a 1 there. They're friends. Or you can go to row 1, column 5. Oh yeah. Oh, yeah. Okay. Nope. There's a 1. They're friends. Now, that's like Facebook. Okay, in Facebook, when you friend somebody, it's bidirectional. If you have to make a friend request, they have to approve it, then both of you have friended each other. On the right-hand side there, that's like following somebody. So like on Twitter, now known as X, or Facebook, when you follow somebody, you can follow somebody, but they don't have to follow you back. Okay? And so that's called a directed graph. And so on the left-hand side there, you've got an undirected graph where it's bidirectional. The relationships go both ways. A directed graph could represent something like one-way streets, right? So if you've ever been to like downtown areas, normal streets, you can go both ways on them. But on a one-way street, you can, like if this on the right-hand side here was a road network, you could drive from 1 to 2, but you cannot drive from 2 to 1. If you wanted to get back from 2 to 1, you'd have to go and make a right turn to 3 and a right turn at 5 and a right turn back to 1, right? Like kind of like in real life. You know what I mean? Like you have to circle around the block if you want to go backwards. So actually fairly accurate, I guess, as far as representing one-way streets there. And so if you look at the directed graph there, 1 is friends with 2 by being represented by row 2, column 1. But if you look at row 1, column 2, it's a 0 because 2 is not friends with 1, the other way, right? The arrow goes from 1 to 2. So it goes from 1 to 2, it's row 2, column 1 to indicate person 1 is following person 2, or there's a one-way street from 1 to 2. Or you understand what I mean? And if you're doing distances, then instead of it being a 1, it would be like 50. It's 50 miles from 1 to 2. So they don't have to be just true or false. You can also have like numbers other than 1 there, right? It is 3 hours somehow from Indianapolis to Lansing, Michigan. You know what I mean? Like somehow, like that's really fast, but or Springfield actually. Sorry, Springfield to Lansing in 3 hours. Definitely got the turbo boost on that one, right? So it doesn't have to be 1s and 0s. Those could actually be numbers. So are the rows discrete people or are the columns discrete people? They're both, because they're both the people, right? Because you got 5 people. So row 1 represents person 1, and column 1 also represents person 1. Nobody's friends with themselves, by the way, right? And so on the left-hand side there, row 1 means person 1, column 2. So row 1, column 2, it's true. That means there's a friendship between 1 and 2. Technically, for the undirected graph, we could actually throw away half of it. We could actually delete half the matrix because it's symmetrical. So we're actually wasting half of all of our RAM here. And RAM is actually the reason why we don't use this. Okay. So, or if we do use it, it's fairly uncommon. And the reason for that is because we've been talking about big O this whole semester, right? So what is the big O time to look up data in this table? You've already got the table. And you want to find out, is person 1700 friends with person 1200? How much time does that take? What is the time complexity of looking up, of search? How long does it take? Order what? Got a big 2D array, and you're like, go to row 1200, column 1700, return the value. How many operations does that take? Yeah. It is not ordered and squared. We are not searching through every element of the table. We just jump to the spot. So to see if person 1200 is friends with person 1700, it is order 1. Time complexity. It takes 1 operation, effectively. In real life, you're going to do some multiplications and things like that, but we don't ever say order 2, order 10. Nah. It's all order 1. It means constant running time. Now, no, it's not in squared. That'd be very terrible if you could, I guess, are you person 1? Are you person 1200, person 1700? Nope. You could do that. That's really, really slow. If you wanted to know if person 1200 is friends with person 1700, you jump to row 1200, go to column 1700, and you look up the number. You don't have to go through every element of the array. Just jump there immediately. Order 1. It's dot at. Mm-hmm. But there's a problem with this, and this is something called space complexity. So space complexity is how much RAM it consumes. So how does the RAM consumption of this approach here increase with the more people we get? So if we have 1 person, we've got 1 element in the table. If we've got 5 people, we have 25 elements in the table. It's 5 by 5. If we have 10 people, we have 100 elements in the table. What is that relationship between the number of people, n, and the number of elements we need in RAM? Big O, what? So if we have 1,000 people, how many elements do we need? If we have 1,000,000 people, how many elements do we need? There's a graph. There's a relationship between the problem size, I'm at the bottom of the screen of the problem size, and the amount of RAM. That's a weird A, but okay, we'll work with it. A, RAM, okay. How does RAM usage increase as problem size goes up? That's what we call space complexity. We don't call it something boring like RAM. Space, right? Because it could be hard drive space, it could be RAM. We don't know. Yeah, it is order n squared, and that's really bad. Because, if you have a small problem, but I mean, nobody cares about small problems, right? But if you have a small problem, if you have like 10 elements, 100, who cares? Nobody cares, right? It's fine for a small graph. But for anything of any size, like if you have like 1,000,000 people in Fresno, you want to write down which people in Fresno are friends with which other people in Fresno, that's a trillion. Like in Fresno's not even like that big a city, like let alone New York, right? Let alone Tokyo, right? Imagine Facebook trying to hold a n squared table for all billion people on Facebook. That's a billion squared. Now, even if you compress it using bit fields and things like that, it's going to be crazy big. Like it's going to be absolutely monstrous when it doesn't need to be, right? And the reason why it doesn't need to be is because you can't be friends with that many people. Facebook actually limits you to 5,000 people. For example, I'm friends with an author called Brandon Sanderson. I helped work on his book tour, and his first book tour, and he was just adding everybody. Like he wasn't a brand new author, but it was the first time anybody had really heard of him. He was brought on board to finish the Wheel of Time series, which you might have seen the TV show on Amazon. It's just terrible. The books are very good, though. And so Robert Jordan, James Rigney, had died, and so the widow, Harriet, had brought Brandon Sanderson on board to finish the Wheel of Time series. Brandon, by the way, is an amazing person. He's an absolutely incredible individual. Huge fan, but also he's just a really good person. So I worked on his book tour. And he added everybody on Facebook, And then what happened was he hit the Facebook limit of 5,000 friends, right? And so every so often he'll go on to, his Facebook and be like, yeah, I got to purge some people. Sorry if I don't know who you are. You might get dropped. I don't know. Just follow me. Yeah, sorry. Yeah, he's a really nice guy, and so he kind of hates doing it, I think. But he'll just go through and purge a couple hundred people, and then add his friends in real life, to it. So Facebook keeps it from being n squared by limiting the number of people to 5,000 times n, right? So the most number of friendships that could exist in Facebook, if there's 1 billion people, is 5,000 billion, 5 trillion. Still a lot. And most people are not going to hit the limit. You know what I mean? Think about intersections. How many intersections can one intersection connect to? All of them? Probably not. On average, how many intersections? You guys tell me. Like if the graph represents, intersections, the right one is downtown, the left one's maybe the suburbs somewhere. How many intersections can one intersection connect to by a road on average? Usually. Oh, there went my tablet. 1 second. Still working. Everything's fine. Okay. 4, right? On average, intersections, you got a north, south, and east and west. Your mileage may vary if you're in New York, which has got Broadway, which is this weird angle street that cuts through the grids. Washington, D.C. has these diagonal roads on them. Let's see. Maps. So if you look at D.C., it's got these like diagonal streets, kind of. So maybe that intersection there's got, I don't know, 1, 2, 3, 4, 5, 6, 7, 8, I don't know, some weird number, maybe 9, but on average, if you're talking about an intersection, it's connected to 4 other intersections, on average, right? There's not that many. It's not 1 billion. It's not 1 trillion. And so using an adjacency matrix is the wrong data structure, right? This is a data structures class. This is the wrong data structure if you're trying to hold like street data or friends. Because most people, aren't friends with every person in Fresno. You're friends with some people, hopefully. Computer science majors, who knows? But, you're friends with some people, not all a million. So the adjacency matrix is only useful if everybody's like friends with everybody. If every intersection touches every intersection, yeah, sure, you use an adjacency matrix. You just suck up the order n squared RAM penalty somehow. But, and, the code is basically just a 2D array, right? But do I not have lists on here? One second. So, if you don't want to have n squared space complexity, you instead use adjacency lists. So if you've got 2,000 people in your system, you create a vector of size 2,000, and each person starts off maybe with just an empty linked list. They have no friends. Or maybe they start off with one friend, Tom from MySpace. That might be too old for you guys. But there was a social network back in the day, and this guy was everyone's friend. I don't know, like you just got him as a free friend. And so I don't know what's happening in this picture. It says Beach, Lindy, LAX. I don't know what's happening. Pasadena. I don't know what's happening there. But everybody knew Tom. Everybody was friends with Tom. So maybe you start off your social network with one person. I don't know. So your list is either empty or has Tom from MySpace. I don't know. And then every time you add a friend, you just push back the friend into the list. Now, a list is going to be fine for small numbers of friends. But once you get up into the thousands, you probably don't want to have to hunt through 1,000 people in the list every time. So you might upgrade to doing a BST instead. So BST, if you have a vector of BSTs, every time you add somebody as a friend, it's an order login time instead of order n, it's order 1 to push back on a list, but to search is order n. And if you really want to be fancy, use a hash table. So hash table is order 1 friending, order 1 unfriending, order 1 searching if somebody's your friend. Or you can just use a vector of vectors, I guess. I don't know. If it's small. So lists or vectors would be the right choice. If you're expected to have small numbers of friends, like intersections, I'd probably use a list. Maybe a vector. I'd have to profile it, see which one's better. Lists are nice in that, forward lists, singly linked lists are nice, especially at least on Windows, in that they don't require any RAM. So if you've got a lot of intersections, or if you've got a lot of people that have no friends, then you might optimize by using a single linked list. It's just a null pointer, basically. It just kind of depends on your demographics, like how many friends do people have on average, that kind of stuff would depend on which one of these options here you care about more, and also whether you care more about running time or the amount of storage that it takes. All right, so trees are a form of graph. So this is a binary search tree. It's a directed graph. It's got arrows on it. It's ordered left to right, but it's got no cycles in it. So this is something called a DAG, a directed acyclic graph. So you've already worked with that. There's 2 ways of traversing a tree. You guys already know depth first search, where it prints everything out in order, right? 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. You go left, you go left, you go left until you run out of lefts, and then you back up and go right. Breadth first search, though, is a different approach. So breadth first search, you start at root, and you print the root, so you print 7. And then you print everybody that's 1 away from the root. So you print 7, then you print 3 and 12. And then you print everybody 2 away from the root. Print 1, 6, 9, 13. You print everybody 3 away from the root. 0, 2, 4, 8, 11, 15. Do you understand? It's like concentric circles going outwards. Breadth first search, rather. Or if you're looking at a tree like this, you're just reading it left to right, like you're reading a book. So that is breadth first search. And breadth first search is actually pretty much the same thing as Dijkstra's shortest paths, as long as everybody has the same distance. So if we have an illustration here of depth first search versus breadth first search, you see in breadth first search, it goes outwards radially. So it starts by marking everybody one away from the root, the start. See? Then it marks everybody 2 away, then marks everybody 3 away, then marks everybody 4 away. So it's like concentric circles going outwards. And so what you get here at the end on the right-hand side is each one of those routes you see there is actually the shortest path to the start. The start is this one, kind of right there. So what you have here is actually the fastest route to every city on our road network here. So we've actually solved the shortest paths problem for every road having a distance of 1, basically. Now, depth first search, you see how it goes left, goes left, goes left, goes left, or maybe it's making right turns, I don't know, from the perspective. But you see it goes deep all the way down, then it backs up, then it goes deep another way. So these are 2 different ways of traversing a tree. They take the exact same amount of time. You don't, if you just want to print everybody out in your graph, they'll both give you all the nodes on the graph. It just kind of depends what you want. So breadth first search is kind of useful. Like if you know that you're searching for something nearby, right? Like that the enemy is nearby, you probably want to do breadth first search because you're going to search 1 square away, 2 squares away, 3 squares away, 4 squares away. Oh, there he is. So there's different advantages and disadvantages, but they have the same running time of them. All right, so let's talk about the next thing you guys need to know, which is Eulerian versus Hamiltonian paths. Okay, and cycles. So a path means you walk through a graph. And the type of path you're doing is either going to be called a Hamiltonian path or a Eulerian path. Okay? A Hamiltonian path visits every vertex once. A Eulerian path visits every edge once. All right? So let's take a look at this. So who wants to go first? Somebody volunteer. I want you to be brave. This is room 1, room 2, room 3, 4, 5, and the outdoors is 6. All right, Olson. Now, Hamiltonian paths, solving the Hamiltonian path problem is actually extremely difficult. It's actually a order 2 to the n running time. So solving the Hamiltonian path problem is order 2 to the n. It's extremely difficult. Eulerian is actually order n, maybe, solve it. So for the Hamiltonian, Luke, what you have to give me is, let's start here. It actually doesn't matter where you start, but let's start in room 1. And I want you to give me a path. A path means you're going to enter every room exactly once. No backtracking, no duplicates, can't go through walls. Give me, what room do you want to move to? You're in room 1 right now. You have to reach every room exactly 1 time. It's an extremely difficult problem. Where do you move to next? 4, okay. Where do you go to next? 2. All right, where to next? 5, all right. Where to next? 3. Next. 6, well done, sir. Well done. Round of applause for Luke. Extremely challenging problem. You guys see what he did? He visited every room on the graph exactly once. That is called a Hamiltonian path. It's extremely difficult. It's an order 2 to the n problem. In fact, a Hamiltonian path is so hard that people actually use it for authentication. So what you can do is you can actually start with a graph that you have connected like this with just a node and a vertex, building, a single path through it. And then you can add complexity to it. You can add additional vertices everywhere. And you can actually make it so complicated that nobody can solve the problem. But you've solved it because you started it, right? You actually have the original path already written down somewhere. And so what you can do is you can hand somebody the puzzle, and it's unsolvable in any amount of time. And you can say, one day I'm going to return to you, and I'm going to show you the answer to this, and then you will know it's me. Because nobody else can solve it, because it's too hard. It's 2 to the n, right? You make tens of thousands of nodes. Nobody can solve it. Except you have the solution, right? Because you solved it before you added all the extra vertices, not vertices, the extra edges on it. And so one day you return, and you're like, here's the solution. And then they're like, welcome back, sir. You're now authenticated. So it's actually a way that you could do like a cookie, right? So, hey, this is me. The next time you see me, I'm going to present this solution to you again. And then they're like, welcome back, sir. It doesn't matter what computer you're on. Doesn't matter your IP address. You present the solution to that Hamiltonian problem, and they instantly know it's still you. Pretty cool. Now, Eulerian is much easier. Okay, so the Eulerian problem is order n complexity-wise. Now, the reason why Luke was able to solve it so quickly is because with a very small problem, it's pretty trivial, right? You just be like, whatever. All right, so Eulerian. Who wants to go? Jarek. All right, so Jarek, let's start you off in 1 again, and you are going to do the Eulerian path. So a Eulerian path. So Hamiltonian means you visit every room. Eulerian path means you go through every door, right? So you go to every room once on a Hamiltonian path. On a Eulerian path, you have to visit every door once. Okay, so let's start you off in 1. It doesn't really matter. And then 6 is again the outdoors. What room do you want to walk to? Can't go through walls. You can't repeat. You can't go through a door twice. There's no 3-dimensional traveling, no teleportation, no quantum effects. All right, so we're going to walk through the door to the east, and we go to 2. What now? Which way do you want to go? 3. All right. We've now cleared 2 of the doors. Only 10, 12 more to go. Which way do we go now? 6. All right. Which way now? All right. We're in 5 now. All right. I will take pity on you. It's not solvable. And the reason why it's not solvable, and I know that it's not solvable, is because it's not possible. Let's look at the degree. How many doors does this room here have? The top left. How many doors does it have? What's the degree of room 1? 4. Okay. What's the degree of room 2? 5. What's the degree of room 3? 4. What's the degree of room 4? And room 5? And room 6? 9? Am I counting 9? I think it's 9. Okay. So, this is not solvable because the guy who came up with the Eulerian path was a guy by the name of Euler. And why is it called a Eulerian path? Because he walked around his town. And whenever he walked around his town, he would try taking every bridge once. So, like, let's say he started off down here in B. And so he's like, today for my walk, I'm going to take bridge A. And then I'll take, bridge D. And then I'll take bridge C. And I'll take bridge E. And then, shoot. I'm home, but I forgot to take bridge G. And it bugged him, right? Because he wanted to take every bridge. And he eventually realized it was unsolvable. Because, here's his key observation. Because, let's look at the degrees here. So what is the degree of C? How many bridges connect to C? Good. How many bridges connect to D? 3. How many bridges connect to B? 3. And A's got 1, 2, 3, 4, 5. So here's the thing. It doesn't matter where you start, by the way. It's not solvable. And the reason why it's not solvable is, let's say that you've got, it doesn't matter which way you leave and you come back, right? You leave one way, you come back another way, it doesn't really matter. That just consumes 2 of your exits, right? Every time you shake hands with somebody, that consumes 2 hands, let's say. Okay? And so A has just lost 2 of its bridges. C has lost 2 of its bridges. Now you can leave from C because there's 1 bridge remaining. So C has to either be your start or your end, right? If you've got 10 bridges, it's not a big deal. You can leave and come back, leave and come back, leave and come back by whatever means you want. Not a problem. You eventually, leave and come back. All right. If you have an odd degree, though, you leave and come back, you leave and come back, you leave and come back, and you got 1 left over. That has to be your start node or your end node, because you leave and you can never come back to it now. If you leave and you never come back, that had better be your start. And if you arrive and never leave, that had better be your end. Otherwise, you're stuck. And the thing is, you can only have 1 start and 1 end. So if you have more than 2 nodes that have an odd degree, it's not solvable. Because no matter how it happens, you're going to leave and come back, leave and come back. You're going to have an odd one left over. Like we had the one between C and D left over. Because no matter how many times you leave and come back, if you have an odd degree, you'll leave, and then there's no way to return to take that last bridge. Does that make sense? So if we go B to D to G to C to D, shoot, we're stuck, right? Or if we don't take D, then you know what I mean. Then we can come up here. Now we're stuck and we don't have E, right? No matter how you leave and return, you're always going to have an extra bridge left over if it's not if it's an odd degree and it's not your starting end. Does that make sense? So it's pretty easy. It's pretty easy to look at. That's why I said it's very simple to tell if a graph has a Eulerian walk on it, because you just look at the degrees of the graph. If everything's even, yes, it's solvable. If everything's odd, no. It's like, let's take a look at, you can only have 2 odds. 2 odds, the start and the end. They can have an extra one, because you leave, you come back, you leave, come back, you leave, come back, you leave, come back, and then you leave. That's your start. For the end one, you leave, come back, leave, come back, leave, come back, leave, come back, and you arrive. That extra one, that odd one, start, end. You have 2 odd ones. Either everything's even, or you have the two odd ones. So let's take a look at this one. Does this one have a Eulerian cycle? Think about what I just said. The rule is for Eulerian, either all even degrees or 2 odd. So is this solvable? How do you give me the proof? How do you know this is not solvable with a Eulerian cycle? Many odds. How many of them are odd? Too many odds. There are more than 2 odds. How many of them are odd? What do you think? At least 7? I think all of them are, right? I don't think any of them are even, actually. It is quite unsolvable, as far as I can tell. So, as far as I can tell, this is the least solvable Eulerian one possible. Now, for Hamiltonian, here's the answer for the Hamiltonian. I'm not going to force somebody to be like northeast when it's online. In person, I had them solve this in person, but online, I'll just give you the answer to that. What about this one? Is there a Hamiltonian path? Is there Eulerian? This is your quiz for today, basically. So, is there a Hamiltonian path? Is there a Eulerian path? What do you guys think? This looks very similar to the other one, right? Slightly different. So examine it. Tell me what you think. No Hamiltonian path. Hamiltonian path means you visit every room once, right? So for Hamiltonian path, you have to visit every room once. A cycle means you leave and you return to the original one. Eulerian path means every door once, right? Every edge is taken once. Hamiltonian for sure. Yeah, here's the Hamiltonian. All right, done. Oh, that's a cycle actually, because I ended up outside. Whatever. Just stop. Just stop here. Yeah, there we go. There's the end. There's the beginning. That is now a Hamiltonian path. Nice. If I went outside, it'd be a Hamiltonian cycle because I ended where I began. What about you learning? So, who wants to do this one? Viale, let's have you do it. Yep. So we got room 1, 2, 3. Actually, this is gonna take forever. I'll just solve it. There we go. Technically works. Let's see if I can do that a little bit neater. Let's see here. Okay, we'll zoom out here, zoom out here, zoom out here. See if I can make it a neater one. There we go. Done. Okay. Was that even right? Yeah, you are correct. There is a Hamiltonian path. There is a Eulerian path, and we know that there's a Eulerian because everything's even. All the degrees of all the rooms are even. So this is a famous philosophical problem, mathematical problem, called the Bridges of Königsberg. But I call it the Bridges of Kingsburg because here in Fresno County we've got Kingsburg, and Königsberg means Kingsburg. So whether or not you call it Königsberg, by the way, or Kaliningrad, is actually a politically charged decision. Just like if you call the capital of Ukraine Kiev or Kyiv, indicates whether or not you're Russian or Ukrainian. So I just call it the Bridges of Kingsburg instead of Königsberg or Kaliningrad. All right. So yeah, you got to do Hamiltonian and Eulerian paths on your homework. BFS. Yeah, yep. Okay. So somebody demonstrate. Who wants to go next? We got more people that are active right now. Who has not gone yet? Sabrina, you want to go? We'll start you. Sure. Okay. So we'll start you in the middle here. And so the rule for depth first search is go left every time. Every time you get a fork, go left. And if you ever hit a dead end, backtrack and go right. So which direction do you want me to go from here? I could go north, northwest, left. Okay. So we're going to go this way. Okay. Which way do I go here? Left. All right. Which way do I go here? Straight. Actually, I would say go left again. Right. That's the rule. Which way do I go from here? Imagine you're in a car, right? Left again. I'm sure you're going to get bored typing that. Which way to... Now, I can't go left here because we've already been there. We're trying to traverse the tree. The graph. We're trying to visit every node exactly once. So if we've already visited it, which the route has been visited, we cannot go there again. So we can't go left this time. So which way do we have to go? Right. Exactly. Then we've got left up this way or right up this way. This is left. This is right. We go left again. Good. And then we've got another left. We got another right. Go left again. She's going to get very bored, I think, typing this. Left is to the root. And so this time we have to go right. And then left is over here, or right is over here. We go left again. Good. It is like a puzzle. It's like a maze, in fact. And then left again. Good. And then which way to go? Left again. All right. Good. And then we can make it left this time. Good. And then which way do we go from here? Left again. All right. Great. All right. And then from here, left is going to the root. So this way is left. That way is right. So this time we have to go right. And then this way is left. This way is right. Okay. Left again. Good. All right. And there we go. We're done. We have now visited every node on the graph. Good. Round of applause for Sabrina, please. And who wants to go next? Stevie. You can go in any direction as long as you don't repeat visits. You cannot repeat. That's the core rule. But the rule for this DFS is always make a left turn first. Then if you get stuck, you back up and you go right. Now for BFS, Stevie, why don't you go first? Why don't you go on BFS? So we're going to start here at the root again. Make a nice little circle here or something like that. Happy little circle. So with BFS, you first connect everybody that is 1 away. Then you connect everybody that's 2 away. Then you connect everybody that's 3 away. So which one should I connect first, Stevie? Sort of really. Which one should I connect? That I should add to my graph. Let's start with the right one, okay? So you are now connected here. Now who do I add? So do we continue from here? Or do we go back to the root and add another child to the root? Go back, exactly. Because we have to add everybody that's 1 away from the root first. Okay, so who do you want to add next? Left, all right. Does not actually matter which order you do this in. So we're just adding everybody that is 1 away from the root. Okay, which one do you want to do next? There's 3 more options. Doesn't matter which order you pick, just pick one. Bottom left, cool. Next. By the way, we're creating a summoning circle from Full Metal Alchemist. So we're about to do some human transmutation up in here. Which one next? Straight. Okay, straight I assume is up. My tablet's not reading. Okay, here we go. Some homunculi, stuff like that. Which one now? Now bottom right. Cool. Okay, now let's go back to here. So which nodes do we connect to this guy with the arrow? Who do we hook up now? We've got everybody that's 1 away. Now we need to hook up everybody that's 2 away. So which way do you want to hook up first, north or south? South, okay. That guy's hooked up. Now, should I keep going south? No, because this guy is 3 away. That would be 3 away. You have to finish hooking up everybody 2 away. This guy's 1 away. This guy's 2 away. So we have to hook up this guy instead, all right? And then this guy will hook up to here. That's 2 away. That's 1 away. That's 2 away. This guy is 1 away, 2 away, 2 away, 2 away, 2 away, 1 away. And so that guy is not actually going to be hooked up to the one we were on. It's going to be hooked up to the other one because it's only 2 away from the root that way. And so what we've done here is we've actually solved the shortest paths problem. Okay? So for every node on that graph on the right hand side there, we now have a route showing if you have to go to the home, province, the capital city of the Full Metal Alchemist world, how to get there. Okay, the highlighted marks on there are the shortest route to get to the evacuation center in case of a hurricane. So BFS is the Dijkstra's algorithm for graphs that all have a length of 1, for every edge being a length of 1. What if you have real life where you've got, things, this is again, everything's a length of 1, Dijkstra's and BFS are exactly the same. What if you have something like this, where you've got a situation where, nodes are 9 miles away from each other, 10 miles away from each other, 7 miles away from each other. Then we need to use a more complicated algorithm. And this more complicated algorithm is called Dijkstra's. And this is the last thing that we're going to learn on graph theory today. And it's a little bit complicated, but it's not too bad. So let me just pull up a notepad here. I'm going to actually probably write on the thing. Here's Dijkstra's algorithm. Dijkstra's algorithm. Okay, to start, choose a node and add it to the to-do list. Sometimes called the to-process list, but to-do is shorter. So you're going to start off with a to-do list, which is going to be a priority queue, sorted by distance from root, and we're going to have a processed list, which is a hash table of nodes to ignore. Okay, so to start with, so we've got two data structures. And these are both data structures that we have studied in this class. So the first one's a heap, and it's everything in the heap is going to be sorted by how far away they are from the starting node. Okay. And the second data structure is a hash table. And so with the to-do list and the process list, we can actually solve this problem quite easy. So we're going to start by choosing a node and adding it to the to-do list. And now that node is going to be where we're driving from, right? We're going to find the shortest path. It's like if we're going to choose A as our start, we're going to find the shortest route from A to every graph, every point on the graph. We're going to search not just from one to one, like we're not going to search the fastest route from Fresno to Bakersfield. We're going to search for the fastest route from Fresno to every city in the country. Okay, that's Dijkstra's algorithm. Like I said, there's another algorithm called A-star where you do much less work than that. But what's cool about Dijkstra's is that you can run it like, the road network in America doesn't change that often, And so you can just run it overnight at Google and solve Dijkstra's, the fastest route, the shortest route from every intersection in America to every intersection in America. And then when people navigate, they can just pull up the answer. You don't actually have to do any calculations. It's already pre-calculated. The only thing you might want to layer onto it is traffic data, right? So temporarily you could have traffic in one place and you might need to reroute. Okay, so let's run through this. So the actual algorithm itself is this. Do until to-do list is empty. Step one, pop off the to-do list and put it on processed. I'll capitalize these. And then two, add all of that node's children to the to-do list. That's the algorithm. That's the whole thing. Okay. The heavy lifting is going to be done by the heap, and the heavy lifting is going to be done by the hash table. So the heap is going to be constantly keeping all the nodes sorted by closest to furthest away. And this is actually the proof of correctness for it, because if we ever pop somebody off the to-do list, you're like, well, how do I know that's the shortest route? If there had been a shorter route, it would have come off the priority queue already, because the shorter route would have gone to the front. It's a min heap. It sorts it smallest to greatest. So let's instead of just giving you the algorithm, let's actually do one. So let's come over here and let's maybe, I'm going to change this weight here to be a 2. Let's make it a little bit more interesting. Okay, so we're going to start off with from A, right? This is our start over here. We're going to start from A. So what do we do? What do we do with A? You guys remember? How do we start? How does the algorithm begin? Remember what we do? We add A to the to-do list. Okay. So we've got a to-do list, and A is on it with a distance of 0. Our process list is currently empty. Okay, now we begin. So what do we do? What's step one? Wallace, what do I do? Tell me what to do. We're currently processing A, right? So what do we do? Begin. What do we do? Go to node 2? We don't go to node 2. What we do is we pop A off the to-do list because it's at the front of the heap. We add it to the process list. Now we're going to add all of the children of A. So who are the children of A? Who is connected to A on the graph? Let me give them some letters maybe, okay? So we got, this is node B up here. This is node A. Let's call this guy D, E, F, and C maybe. So what are the letters of the children of A? D, E, and F, right? So we're going to push D onto the to-do list with a distance of, how far is D from A? 14. Okay. We're then going to push E with a distance of 9 and F with a distance of 7. Now it's a min heap, so which one is going to come to the front? Who is closest to A? F. That's correct. So, and then heap will keep these guys sorted from smallest to greatest. Okay. Good. Wallace, you have completed step 1. We're now going to repeat. So, Viale, who gets popped off the front of the list now? Who's the next node we're going to process? Remember, when you pop off a heap, you always get the minimum value on a min heap. Okay? Yeah, we're going to pop F, right? So F comes off the to-do list, and it gets added to the process list. Okay? And so we can visually represent this. Sometimes it's called the frontier or something like that. But we basically represent it. Yeah, you can see the animated GIF here is turned it red, right? And so we know that this guy, that's the shortest route. There is no shorter route to F, because if there was, we would have taken it already. And you can think about it logically, like the only other ways out are 9 and 14. It is impossible to get to F shorter because we do not allow negative numbers. Okay, Dijkstra's does not work with negative numbers. Okay, so the shortest route is guaranteed to be that way. Okay. And then it's going to add in who. So we've got C. We don't have, C is not 15 away from root. Remember, the numbers are how far it is away from our starting city, not how far away it is from F. How far away is C from, how far is away from C from A? 21. Mm-hmm. 22. And what's the other child of F? What's our other child? In fact, let's make this a little more interesting. Make this just 1. Okay. Remember, you have to add all of your children that are not on the process list. So yeah, so that is going to have E on the to-do list twice. That's fine. That's what the process list is for. If anybody ever pops off and we were like, oh, we've already processed them, we just throw it away. Okay, so now we've got E twice in the to-do list, and that's fine. Because there's always the possibility that you find a shorter route until you've processed everybody shorter than you, right? There's always the possibility a shorter route exists. For example, E is 9 away from the start, but by going through Flagstaff, we found a shorter route to Phoenix or something like that. You know what I mean? So it's 7 to F and 1 to E that way, and so it's 8. So we now pop off the front of the list. So E gets popped off. So we now know the shortest route to E is 8. There is no faster route. There's no fast route. If there was, we would have been there already. So where's my mouse? There it is. So we're going to add E in here. And so E is officially 8 away. F is officially 7 away. A is officially 0 away. Okay. All right, so this guy is now processed. This guy is now processed. So who are the kids of E? How many people are connected to E? Give me their names. D, B, and C. B is not connected to E. So yeah, D is going to get added at a distance of 10. So we've just found a shorter route to D. And C is going to be added with a distance of 19. Shorter route to C. B is not connected. We do not have a line between E and B. And A and F are already on the process list. Remember, anytime you're looking at a node, you can check the hash table, order 1, very cheap. Hey, have I seen that F person before? Yep. Throw it away. Don't do it. Okay. That stops you from getting infinite loops. All right, so that one's done. So Olson, you're up next. What do we do next? Here's the algorithm. Pop off the to-do list, add all of its children. That's the entire algorithm. Pop off the heap, add all of its kids. Keep doing that until you're done. So which one do we pop off now? And if you ever encounter a node, either off the front of the to-do list or adding children, if you ever encounter a node that is already on the process list, discard it. Just don't do anything. So yeah, exactly. So we are going to pop off E9. We're like, oh, we've already seen E before. Throw it away. Boop. Now we're going to process D10. Very good. So D10 comes off the to-do list. It goes onto the process list. Just two hash, like a hash table and a priority queue. These are standard library functions. You don't even have to write them. Push and pop. This whole algorithm is about this big, even though it's very complicated. When you look at it, and it's actually like not that many lines of code because the heap and the hash table are doing all the hard work for you. So we've just moved to do D10 to process. Now we add all of D's kids. So how many kids does D have that are not already processed? So D, by the way, is now officially 10 away. So that is the route that we took. So you have been processed. So how many kids does D have that are not already processed? Only B. That is correct. How far away is B from root? So we're going to add B to the to-do list. How far away is it from the root? 19? I think so. Okay. And then the hash, the heap will sort this like that. It doesn't matter which one, if there's a tie. It doesn't really matter. And we're done. So that is it for D10. This is embarrassing. What's embarrassing? Oh, just because of the math. All right, Kevin, you got to do the next one. So we've got D at the front of the heap. What do we do with that? We've already seen D. So what should we do with this guy? Throw it away. We pop off. Oh, D. Oh, we've already. Next. Discard. Grab the next one. Okay, so the next one we're going to grab is C. So that one comes off the priority queue, goes on to the hash table. By the way, this is our answer. These are the shortest routes from A to every city. So C's official distance is 19. So C is officially 19 away. And we got there via this route here. Okay. And now we're going to add all of C's children. So how many children does C have, Kevin, that are not in the processed list already? How many cities are connected to C that are not already processed? Nope. B is not processed yet. B is in the to-do list. But there's a possibility we're going to find a faster route. You know what I mean? Like we found a faster route to E via F, right? So we have not processed B yet. There's still a possibility that by coming through C, we're going to find a faster route to B. In this case, we're not. But yeah, so we need to add B. How far away is B from A via C? C is 19 away. B is 6 away from C. 19 plus 6 is... Ada? 19 plus 6. 25. Very good. Okay. So we are going to add B in the distance of 25. As it turns out, it is not closer, but you just got to do the math and see how it works. Okay. So the last node is now going to get processed. So B is going to come off the to-do list, go on to the done list, the process list. And this guy is going to have a distance of 19. And we're done. That's the whole thing. Every city now has been processed. And we're not done yet, though. We're not done yet. Because the to-do list is not empty. So we come up here, and we're like, C22, C22. Oh, we've already processed C. Throw it away. Pop. Done. And then we grab the top of the heap again. B. We've seen B. Throw it away. To-do list is now empty. Why do I keep saving this? Keep hitting save. Yeah, this is Dijkstra's. Dijkstra's. D-I-G. Dijkstra's. There you go. I keep reflexively hitting save on this. And that's our answer. Okay? So that is how far away each one of the cities are from A. That's the whole algorithm. So you're going to have like a bunch of calls to, I don't know, hash table.contains. You're going to call heap push and heap pop and heap top. And hash table insert. That's it. That's the whole algorithm. And you can use this to find the shortest paths on any graph. There's a modification for games and other things. Robotics uses it a lot, called A-star. But that's it. So for your homework today, you're going to have to be able to do Dijkstra's algorithm. You're going to have to be able to do a Eulerian you're going to have to be able to tell if a graph has a Eulerian path on it, Hamiltonian path. You have to know what the degrees, I guess. So the degree of this room here is 4, whatever. And that's your quiz for today. That's it. So hope you guys had a good time. Graph theory is a lot of fun. It's very useful. Like I said, we're not really doing coding today. It's just all high-level conceptual stuff. But it is very useful. Graph theory is amazing. I love it. It's one of my favorite branches of mathematics, right after linear algebra. Linear algebra is my favorite. Linear algebra is like algebra, but just more of it. It's more linear. No, it's just more algebra. Ada, you love algebra, right? Should you love algebra?
No. Yes.
Yes, no, yes. What was your favorite mathematics? Addition?
When it made sense.
When it made sense?
Yeah.
What about negative numbers? Do negative numbers make sense?
Yes and no.
Yes and no. What about imaginary numbers?
No. Numbers themselves don't really make sense.
Negative.
They go up through infinity. I just have to comprehend.
Comprehending infinity is fun. All right, so that's it for today, guys. Thanks for coming out, and I will see you on Monday. Get your projects done. Work hard. Peace.